So we say that a Turing machine M decides a language L in time t of n if for every word in the language, if the size of this word is n, that word can be decided in at least t of n moves, at most, sorry. So if M is not deterministic, that's for a deterministic machine. If M is not deterministic, this implies that for every W in L, there is at least one sequence of moves of less equal or less than T of the size of W. That leads to the acceptance of T of N. It will be more clear if we have here N. Here N. Okay. And that the Turing machine holds on all inputs in time T of N. Okay. So is there any questions about this definition? So we saw some examples, for example, for this AN, BN. For this language, what would be the time that a Turing machine can decide this language, AN, BN? Any idea?
T of n, because I think that we made an linear algorithm.
Yes, exactly. Okay, so second definition, a language L is said to be a member of the class D time for deterministic, the D is for deterministic time T of N, if there exists a deterministic multiple tape Turing machine that decides L in time O of T of N. So for example, last class we argued that the SAT problem can be decided in deterministic time of order 2 to the n. Okay, and that's for deterministic time. Remember, trying all possible paths, all possible assignments to the formula. So, questions here? No questions? Alexander, no questions?
Profe, cuando dice el tamaño n, ¿se refiere al tamaño de toda la cinta o al tamaño de, bueno, a la cantidad n? Que por ejemplo está
for example, if this is n in general in complexity theory, n it refers to the size of the input. So you will have a Turing machine here, and in the beginning, in the very beginning, you have an input here, right? For example, 0, 1, 0, 0. And let's suppose that this input is called W. So this n refers to the size of W, okay? N is the size of the input. So remember we wanted to know if the size of an input was a power of 2, that we have to go divide by 2, divide by 2, divide by 2 n log times. So in that case, we say that that language was, if I remember correctly, n log n. That means that for any input of size n, the machine will take n times log n to decide if the string is accepted or not. Do you understand now?
Sí, profe.
Nicolás, Are you okay with this?
Yes.
Okay, good. So here, okay, we need to define this other one. Oops, sorry. We say that a language L is a member of the class N time T of M if there exists a non-deterministic multi-tape Turing machine that decides L in time O of T of M. Okay? It's the same, but it's called N because the machine is non-deterministic instead of deterministic. So the following must be something clear for you. So the set of languages that can be designed in deterministic time T of N is a subset of the set of languages that can be decided in non-deterministic time T of N. Anybody sees that or why?
Profe, pero el dead time de TDN no debería ser un número, o ¿a qué refiere cuando dice que es un conjunto?
Okay, good question, excellent question. No, because look here, this is defined as a set. Look, a language L is said to be a member of the class D time T of N. So this language is a member of this. That means that this guy is a set. This guy is the set of all languages that can be decided in T of N. For example, just to give you an example, we have the time n log n. So we saw in class a language that can be designed in deterministic time by a deterministic machine in time n log n, right? And that language was this one, for example. L1 is the set of all strings in some alphabet, zeros and ones, such that the size of x is of the form 2 to the m for some m. This language can be decided, so to know if a string belongs to this language can be done in n log n. We saw that, remember? But this is not the only language that can be decided in n log time n. For example, I put the set of all this language, L2, can also be decided in n log n. It can actually be decided in n, but that means that this is all, because this is like a, if it can be decided in n, it can also be decided in n log n. So this means that these two languages are here in this class of languages, okay, in this set of languages. And there are infinitely many more. So this is a set. So the question here, and it's the same here, there are many languages that can be decided in non-deterministic time T of N. But what seems to be a property is that every language that is here is also here. Do you have any idea why?
I think that it's because any any deterministic machine is also a non-deterministic machine that don't explode that non-deterministic property.
That has one choice at in every moment. Very good.
Yes.
Excellent. And this other property, which is I'm gonna write it a little bit better. It says, if this happens, then this happens. So if T1 of n is of the order of T2 of n, then the set of languages in d time T1 of n is included in d time T2 of n. Any of you see why?
Because the time T1 of n is less than O big of T2.
Exactly, that's the reason. And implicitly, I use this property in this example. I didn't plan for that, but I use this example here because I said this. I said, in class, we saw that L1 belongs here, right? And now I'm arguing that L2 is also here. But what we know for sure is that L2 in class 2 can be decided by a deterministic time Turing machine in N, right? That's what Juan said. But since N is of the order N log N, and L2 belongs here, then L2 also belongs to this one. This is what this theorem is saying. So since L1 is here, then L1 is also here. Do you understand that? Okay, this is more interesting and much more complicated to show. So look what it says here. The deterministic, every problem that can be decided in NK by a deterministic Turing machine, every language, can also be decided in deterministic time NK plus 1. That's obvious, right? But it's not only about inclusion. Look what happens here. This one is not saying this. It's saying this, that the inclusion is strict. So because the inclusion is strict, can somebody tell me what that is saying?
Porque ya es otro nivel de tiempo. O sea, como que si esta toma me multiplico por mí mismo n veces, ¿no? Pero multiplicarme otra vez por mí mismo ya es como otro nivel mucho más allá de tiempo.
Yeah, that's the intuition, but look, to prove this, what you have to do? To prove that for every L, that if L belongs to the time NK,
Yo lo que haría...
Wait, give me a second. Then L belongs to the time NK plus 1. That shows that if L can be decided in NK, then deterministic time, then L can also be the time nk plus 1, n to the k plus 1. But that part is easy. I mean, it's trivial. But what else do I need to prove to complete this?
Yo lo que haría es literalmente demostrarlo desde el punto de vista de compararlo de que uno es menor que el otro. Entonces cancelo, me quedaría uno menor a n, pero yo sé que uno nunca va a pertenecer nunca va a ser del tamaño de n. Entonces, pero es que yo digo que es que n es de un valor mucho más grande. Es que no sé cómo
No, but
explicarme.
look, I mean, these are set of languages, like the elements in the, and also here, the elements of these are languages like this, problems like this. You see, you have to understand this. It's like a language is basically a problem. What's the problem? Maybe somebody can tell me what's the problem related to this language. Can somebody tell me?
Pues, profe, ahora me he confundido con la parte de que un lenguaje con tiempo n a la k es subconjunto de un problema, un lenguaje.
No, these are set of languages, not languages. Set of languages. Yeah, Nicolas is right. So, but set of languages. Do you understand? Look, I'm saying that L1 belongs to this. But before that, I think you are having problems. You all having problems with the notion of languages being problems. I mean, when I say that L1 belongs to this L1 here, belongs to deterministic time n log n, can someone please tell me the meaning of that?
Sí, significa que el lenguaje se resuelve con un tiempo n por
Exactly. And what does it mean? Exactly. And what does that mean? I mean, the last thing that you said, that it can be that the language can be decided in n log n. What does it mean? That's the last part that you should, and that's the problem.
Sí, pero
It means that given a string, you should decide if the string belongs or not to this set. So for example, that means that I give you a language here, I give you 0, 1, 1, and the machine can decide that this is not in this language in n log n for n equals 3. Okay? That's why every language has a natural decision problem associated to it. You need to decide if an input belongs or not to that language. Is that clear or not? That was basically what Alexander said.
sí, profe, esa parte sí la entiendo. Lo que
Yeah,
no
no,
entiendo.
you got it. But I think maybe was who talked now. Maybe Betancourt asked the question.
No.
Give me a second, guys. Okay, guys. Sorry for that. So Betancourt, you asked some question, right? About this. So what you have to prove here is that every language that is in here is also here. So every language that can be decided in complexity n to the k, it can
Profe,
also be decided in n k plus 1.
profe, mira, mira, mira el chat. Creo que esa es la idea que intenté plasmar ahora.
Yeah, that's the idea, but that's not quite the proof. I'll explain to you what's the difficulty of this proof. I mean, let's go step by step. First, you need to prove this, right? If you want to prove this, you need to prove this. Do you understand that or not?
Yes.
Okay, but that's not enough because that will only prove this. You also need to prove this. Yeah? Elkin?
So we also need to prove that the sets never are equal.
Mm-hmm. Exactly. So you need, basically the hardness of this proof is that you need to prove that it's telling you that there are languages in here that are not here. And what Elkin just said was basically this, that d time nk intersected with d time n to the k plus 1. What can I say about this intersection?
De pronto que la cardinalidad de ese ser resultado no es vacío, o sea, que eso no es vacío.
Exactly. So basically, whatever allows you to say this, because it could be the same. It could be the case that they are all the same, right? Who knows? And that's when you say in complexity theory that that a hierarchy collapses. If the hierarchy collapses, it means that they are all the same, and that's an important problem. So this is the same. It happens to here. We're gonna see that P is included in NP. That's easy to prove, but what they really want to know is that P is strictly included in P. So they will have to find a NP problem that is not P in P. Otherwise, these things might be useless because they might be the same set. So people believe that they are not the same set. That means that this happens, but they don't know. For this, that now they know. They know that there are some problems that, for example, there are problems that can be solved in n squared, but not in linear time. So it can be solved in cubic time, but not in quadratic time, and so on and so forth. Do you understand that? And that's a very important result.
Yes, now I get it.
Okay, good. Let's consider some examples. And we're gonna use a Turing machine with multiple tapes, with 2 tapes. That's enough. So this language, this context-free language, W such that W are sequences of A's and B's. Okay. So an easy way to prove that this is in non-deterministic linear time, that means n time n, is, so that means that this string is like of this form, W to Wm, and then W1 again to Wm, and the size of this is n. So what this can do is the following. The machine non-deterministically guesses the middle of this string. And then it guesses the middle and then compare this with this, this with this, this with this, and with this. And if they are all the same, then it says yes. So the trick, the power is that this machine can easily guess the middle point because it's a non-deterministic machine. So it could say, it could do like decides to say this is the middle or not to say, this is the middle or not to say, this is the middle or not to say. Do you understand this algorithm? Basically, you are given as usual, you are given an array of a vector, and you need to know if this vector has this shape. So you can guess the middle. What you need to compare is the first cell with the cell right after the middle, the second cell with the second cell right after the middle, and so on till the last cell before the middle and the last cell. You understand that?
Yes.
And that can be done, of course, in time, in linear time, because you're just guessing. That's the power of non-deterministic machines. And how can you do it in deterministic time? What would you do?
And we can find
Yeah.
the middle, and then
How
we
do you
go
find the middle? How do you find the middle? That's an interesting question. That's actually a problem. So you find the middle and then you do the same that we said before.
Para encontrar la mitad sería como ir tachando desde los bordes hasta el centro hasta encontrar elementos sin tachar.
Excellent. That's the way. Okay, so that way you can also find an algorithm that solves this problem. Okay, so I'll give you as an exercise some problems, and you need to prove that they are in dead time or non-deterministic time to the end. Okay, so let's go to the most important complexity classes there are. So basically there are two kind of, in complexity theory, there are two important classes of problems. There are the ones that are tractable. That means tratable in Spanish. And the ones that are not. The tractable ones are those in polynomial time. So everything that can be, every language or problem that can be decided in polynomial time is tractable. And untractable means that you are not polynomial. So for example, anything that is exponential is non-tractable or untractable. This is because typically you accept linear algorithms, quadratic algorithms, cubic algorithms, and so on. But of course, that's this problem that we mentioned last time, that it's hard to say that n to the 100 is tractable. I mean, if you have an algorithm that will take that, we wouldn't be very happy of that. It will take a lot of time, right? But in practice, that never happens. I mean, in practice, basically, I'm sure that you have never seen an algorithm that is more than n cubed. Have you?
No, I haven't.
So what's the highest complexity, polynomial complexity that you have seen?
Yo he visto uno en el A5, pero eso fue como en segundo semestre que uno programa asqueroso.
Oh, yeah, right.
Algoritmo húngaro.
Y aún en el quinto no programamos asqueroso.
No, now
Pues
you're
sí,
very
pero
elegant
tan feo.
programmers. Yeah, of course. If you nest loops, you can get any complexity you want, right? Like, I mean, if you do this, that's n square, that's n cube, and so on. I can continue and make the algorithms complex as possible. Even, of course, even if you put I here and J, K, and J here. Okay, so that's the idea. So from now on, we're gonna define this important class at this big union. The P class are all languages, the union of all languages that are in the set d time n to the I. For every I bigger than 1 or equal to 1. So you understand this definition, right? Okay, good. So, and similarly, wait, remove all this garbage here. And this is the all important class, which is the same, is all the languages NP that can be decided in non-deterministic time and to the I mean polynomial time. Any questions about this other definition, NP and P?
Creo que Juan José en el chat puso.
You wrote nasty. I don't know what he meant by that.
No. Le está respondiendo a Gómez.
Okay, so no questions? Okay, so, and we talk about this, right? I mean, this is basically that P is included in NP, and the reason is exactly what Juan Rengifo said before. Because any machine that is deterministic can be seen as a non-deterministic machine that doesn't use that property. Okay, so now we're gonna see some NP problems. Okay, so we're gonna go to, well, we already saw SAT. SAT is a non-deterministic polynomial time. You remember how we showed that SAT was polynomially non-deterministic? Do you remember the strategy? Nicolas?
Yeah, the only way was to generate the tables, the truth tables. So.
Yeah, you just guess one of the assignments, right? And then you check if that assignment satisfies the formula. Any questions there? So here are some other ones. All these NP problems are easy because non-deterministic machines are very powerful. They just guess and verify. That's all what they have to do. Here's another famous NP problem. NP is kind of, it means, especially NP complete, difficult. Here's a problem of that kind. Hamiltonian Path problem. So you have an undirected graph with vertices v1, v2, vn. A Hamiltonian path is a path that passes through all vertices. So, for example, you are given a graph like this. So the Hamiltonian path is you are given a graph, for example, that, and you need to decide if that graph has a Hamiltonian path. The question is, does this graph has a Hamiltonian path? Nicolás?
Sí.
No. Sorry.
Espérate. No.
Sí. No.
Look at, I remind you the definition. So, a Hamiltonian path with this, you have this graph has V1, V2, V3, V4, V5, V6.
Sí es, ¿no? Sí tiene.
Yeah, and many of those, right?
But you revisit V5, no?
But look, V1, V2, V3, V5, V4, V6.
Yes.
Okay, so to prove that, I mean, what would you do with deterministically to know if a graph has a Hamiltonian path? How will you solve this problem with a real algorithm?
It can be. There are not sufficient and unnecessary conditions for determining if a graph is Hamiltonian. So the only way is like try all the possible paths.
And how many paths? How many are there?
Well, what thing? Because a path is a permutation, right?
Yeah, exactly. So a Hamiltonian path is a permutation, of course, because you need to pass through all. So, and there are n factorial permutations. So the brute force deterministic algorithms will give you the answer. But of course, it's very expensive. I mean, factorial is a real expensive function. So how do you think that factorial compares to exponential, like this, to this exponential? Which one is worse?
Factorial. In that case.
Okay, good. So you're in the right track. So just to show you that this is a very expensive solution. Okay, so how are you doing non-deterministically? But so you appreciate the beauty of non-determinism.
Like guess the one that it's Hamiltonian.
Yeah, exactly. You just guess any permutation. You say, I'm gonna take, I don't know. Let's suppose that I'm the non-deterministic person, and I say, well, take V2, V3, V4, V1, V6, and then I just guess that at random, and then I just need to check if that is a valid path, and then that's checking if there is an edge between the nodes I just guessed, and if there is some missing edge, I don't say anything. But if there is no missing edge, I say yes, this has a Hamiltonian path. Do you understand that?
Yes.
If the algorithm that try all paths in the graph is non-deterministic or is deterministic?
If you try all paths, you are normally deterministic, yes. Because remember, the power that you need to associate to non-deterministic, they can guess something and verify. So my argument is the following. I guess a permutation of the edges of the vertices, and then I check if that permutation is a valid Hamiltonian path. And that I can do in polynomial time very easily. So it's non-deterministic polynomial time. Why it works? Because I will never say, for example, no, this, I will never say yes if the graph doesn't have any Hamiltonian path. Because whenever my guess does not work, I don't say anything. And that's good because, remember, a non-deterministic machine accepts when there is a path to the acceptance. And it rejects when there is no path that accepts. Is that clear or you're confused? No, I'm not writing anything. I'm just looking at the graph.
Profe,
Mhm.
o sea, sé que en estos casos cuando nosotros estemos trabajando con si una máquina no determinística bueno, para el caso del Hamiltonian Path,
Mhm.
esta lo único que hace es realizar un solo intento.
Exactly. Just one try, and if that try actually works, it says, yes, this graph has a Hamiltonian path. If that try doesn't work, then the machine doesn't say anything. And that's okay, because that means that if that graph doesn't have any Hamiltonian path, the machine is never going to say yes. And if the machine never says yes, meaning it is rejecting that
O sea,
graph.
él con solo un intento define si falla o acepta.
Exactly.
Ok.
So a non-deterministic machine accepts an input if it has an execution that says yes, so that it goes to acceptance. And a non-deterministic machine rejects its input. The input is the graph in this case. Rejects that input if there is no possible computation that leads to acceptance. So if the machine never says yes, then that means that it's rejecting. You understand?
Yes.
It's like think of a couple. So a girl or a guy, doesn't matter. A girl will reject you if any possible. You'll never forget this way. How do you know that a girl is going to reject you? If whenever you ask, she never says yes. Then you can fairly assume that she's rejecting you. If there is one chance that she says yes, and she says yes, so of course she's accepting you. Okay? The same apply for girls or for boys. So is that example clear? Nicolas? Was that clear now?
Yes.
Okay, so let's continue. So Hamiltonian path is easily proven to be NP. This is a little bit more complicated. We're gonna see that later. The clique problem. So you are given a undirected graph with vertices v1, v2 to vm, and vertices. A k clique, or a clique of size k, is a subset of vertices such that there is an edge between every pair of vertices in that subset. So the clique problem is to decide if for a given k, G has a k clique. Okay, basically you have to find a subset so that all the elements, a subset of the vertices, such as all the vertices in that subset are connected by an edge. Do you understand or not?
No, profe, no lo...
If we can make a subgraph that is complete.
That is right. That's
Okay.
a much, thank you, Juan. That's a much nicer way to put it.
Okay.
Well, k is the size of that particular.
No, profe, no
Yeah,
entendí.
exactly. K complete graph.
Mm-hmm. So, for example, what is it? Here. Look at this graph here, just for an example. V1, V2, V3, V4. So that this graph is not complete, right? Julián
Right.
Paredes, do you see why it's not complete?
Porque no hay una conexión entre V2 y V4, ¿no?
Exactly. So, but it has a clique of size 3. Which one is it? I mean, there is a subset of this graph in which there is an edge between every two vertices.
I V1, V2, and V3.
Mm-hmm. Exactly, this one. You see? So basically, you are given a graph, and you are supposed to find the corresponding clique. Okay. So what is the problem? How you do it deterministically? Well, that's easy, right? You will try every possible subset of the edges, or the vertices, sorry, and then you will verify if there is a path between every two members of that subset. What's the problem with that solution, deterministic solution? Can someone
There
tell?
are 2 to the n possible.
Exactly, there are 2 to the n possible subsets. It's not as bad as the Hamiltonian path, but still 2 to the n is exponential size. So that will give you an algorithm that is 2 to the n, and then checking that subset. And what would be the typical cost checking that if the subset is strongly connected? I mean, if completely connected, sorry.
N squared, I think, because
Exactly.
for each vertex, I have to check the all.
Exactly. So you will get an algorithm that is what is it?
2 to the n.
2 to the n. Something like this, right? How about non-deterministic algorithm?
Lo genero y después reviso.
Exactly. You just, I'm gonna guess a subset, and then you verify, and then that can be checking can be done in n squared, right? And depending on the non-deterministic machine, you can do that linearly or quadratic, but you can just generate. And so in any case, you get a polynomial algorithm. So then we can say that the clique problem, this can be done in deterministic, non-deterministic time, polynomial non-deterministic time, and exponential polynomial time. Okay? Exponential deterministic time. Actually, sometimes you write like this. Is in this and is in this. Is that clear? Because we have an exponential deterministic algorithm, which is where would you write that? Sorry, I lost it, but we wrote it here, 2 to the n times n squared. To prove that this is NP, you can prove that you can do this in the probably you generate and then you verify. So n cubed or even n to the 4, but still polynomial. Any questions here?
Profe, no entiendo muy bien cómo es la parte de clique. El clique solamente es un subconjunto de vértices tales que todos estén conectados o...
Yes, exactly that. Exactly, that's it.
Profe, una pregunta.
Yeah.
O sea, la idea de cada uno de estos es que tenga conexiones n-1. O sea, que cada vértice tenga esa cantidad de entradas, por decirlo así.
That I give you a set. You need to find a subset of the set of vertices, such that if you take any two vertices in that set, there is an edge between these two.
Sí, porque es que, por ejemplo, para un vértice, ¿cierto? Digamos que la cantidad de vértices sean 3, como está acá. Entonces, el número...
Well, is 4. Or you mean the
pero digamos que la parte... Exacto, ese pedazo.
Yeah.
Entonces, el número de incidencias que puede haber hacia un solo vértice serían el n-1.
Where n is this size of here.
Ajá, en ese caso.
Yeah.
Entonces, si queremos, o sea, ahí dice que para cualquier vértice siempre tiene que estar conectado con cualquiera de los otros. Entonces, lo que se podría mirar es que cada vértice tenga n-1 incidencias.
Exactly.
Y ya con eso se resolvería el problema.
No, because you need to find this. What if this is not the right subset? What if there is another subset?
O sea, toca hacer otro conjunto.
Exactly. So in principle, you have to try all the subsets till you find one. And that's the problem, because there are 2 to the n such subsets. You see the problem? Thanks for your question. It was good because people might be confused about that.
Profe, disculpe, a la que hace referencia, ¿se refiere al número de subconjuntos generados o al número de vértices que tiene cada subconjunto?
The second one. The size of that subset.
Entonces, sería, en el caso de que está en el ejemplo, sería un 1 con k igual a 3, ¿cierto?
Exactly. Okay, so list this. I prefer to do the. Okay, now I just show you how to prove that something is P and something is NP. In the next class, we're going to talk about how a problem can be reduced to another. That is called polynomial time reduction. This is similar to what we saw when we are talking about undecidable problems, that you reduce something from something. Here is something similar, but you reduce something to something. But this is a relatively complex problem, so I prefer to do that in the next class to have the 2 hours. Okay, so for now we stop here. Bueno, voy a parar la grabación.